Доброго вечора, українські радіаційні онкологи, медичні фізики. Слава Україні! Дуже дякуємо, що приєдналися до Research Methodology Course for Ukraine. Help Ukraine Group, Austria International Research and Development Committee are excited to present lecture 8 in the course. And our topic is statistics in clinical research 1. And I'm super excited to host two amazing Stanford educators. So the first one is Dr. Kristin Sainani. She's a professor at Stanford University and internationally recognized science journalist and educator. She teaches the widely used Coursera course, Writing in the Sciences, and leads Stanford Online Medical Statistics Certificate Program. Dr. Sainani works as a statistician in sports medicine and serves on the editorial boards of several major journals, including Medicine and Science in Sports, Exercise Sports Medicine, and American Journal of Sports Medicine. She has written extensively about health, science, and statistics for both academic and general audiences. And she's also the co-host of the New Normal Curves podcast that she will tell you about. And Dr. Regina Nuzzo is an award-winning science journalist and professor at Gallaudet University, who specializes in communicating statistics with clarity and creativity. Her work has appeared in Nature, the New York Times, Scientific American, New Scientist, Science News, and other major outlets. Her feature article on p-values in Nature received the American Statistical Association Excellence in Statistical Reporting Award. Dr. Nuzzo has written for the Proceedings of the National Academy of Sciences and for the American Statistical Association. She serves as a statistics educator at Stanford University, where she co-teaches a graduate course in clinical informatics management. She's also the co-host of the New Normal Curves podcast. The Ukrainian community is honored to have you with us today. Unfortunately, many of them could not join because of problems with missile attacks and electricity, but we are very, very grateful to you both for teaching us today, and we are very eager to learn about this exciting topic, statistics in clinical research. I'll stop sharing. The podium is yours.
Thank you, Natalia.
Thank you so much. You got it?
Go ahead. Yeah. So today we're going to dive into some basic nuts and bolts of statistics and hopefully make it a little bit fun. And as Natalia mentioned, both Regina and I are co-hosting a new podcast. Actually, we are on what episode, Regina? 23 now?
24, I think.
24, wow, which is kind of amazing. And it's a free podcast that anybody can access. And our goal is to teach people how to do good research methods, good statistics. So while making it fun, we talk about different papers. It's kind of like a journal club. Sometimes we talk about specific statistical methods, and we've got a whole episode. Our most popular episode is actually on p-values, believe it or not, an hour 13 on p-values, and we've told a lot of stories and made it fun. So we hope that you'll tune in. It's a really good, easy way to learn, very story-based. Anything else you want to add to that, Regina?
No, I think that's it. It is surprisingly fun. Let's just say that. We have a number of people who say they laugh out loud while they're learning statistics. And we feel like, what more could you ask for, right? Of that. So we're going to be going over, as Kristin said, statistics nuts and bolts today. And this is just an outline of what we'll get: descriptive statistics, standard error, confidence intervals, p-values, hypothesis testing, and statistical power.
And we will try to give you a little bit of detail. I think sometimes when these concepts are taught, they're taught at a very surface area, and we want to dig down a little bit deep. That's what we like to do in teaching, but also, keep it understandable. And I thought we would just start with a hypothetical randomized trial. This is totally made up, but just to have a little toy example to play with. Imagine we're doing a randomized placebo-controlled trial in, say, lung cancer patients, and 10 patients are getting a novel radiosensitizer for 4 weeks, and 10 patients are getting some kind of placebo, and the outcome is tumor size in millimeters.
So what's one of the first things you need to do once you have run your trial and you have your data? You look at the results. And Kristin and I are big fans of data visualization. Before you run off and try to get some p-values and things that you can publish, you have to actually look at the data. And what we've presented here are what's called box plots. And you can see the red dots show you where the exact values actually are. That y-axis is talking about what value they are. On the left in the pink, we have control, and the right, we have treatment. And that thick black line in the middle of the box, that's where the median is. That's where the center is. The middle 50% of the data are contained in those boxes, and then we have the tails out to the right. And so we can see here that the mean treatment group size was smaller than the control group size, which is what we want, 43 millimeters compared to 51 millimeters. So that means the difference in the means is 8 millimeters.
And Regina, what I love about this graph is I love to see those individual data points on top of the box plot, because often when, as a statistician, when we're reviewing papers and looking at things, we want to see those, is there an outlier? How are things clustered? We want to see that full distribution. So I love it when authors put the data points on like that. So let's talk a little bit about descriptive statistics, just using this toy example. So we have another way of displaying the data that I love, which is histograms. And you see this is just for the control group on the right side of the slide. So this is showing how frequent different ranges of tumor size exist. And it's a little bit arbitrary how big we make those bin sizes, but it allows you to see another way of looking at the distribution of those data. So again, the control group just had 10 people. The mean, which is sort of the balancing point of, if you imagine kind of putting a fulcrum and balancing those masses, that would be at 51. The standard deviation is 13, and we're going to spend some time talking about standard deviation. Standard deviation is a measure of how variable, how much variation is there in tumor size. So the kind of average variation here is about 13, and you can see that because a lot of people are, 10 away from 50, right? And some people are a little further than that. As Regina already said, the median here was at 49, and median means half of the people are less than 49 and half of the people are more than 49, which makes a nice clean statistic. Statisticians also like to talk about the interquartile range. So this corresponds to the box we just showed you. The first quartile, meaning the 25th percentile, where 25% of people are lower, was at 44. And the third quartile, meaning 75% of people are lower, was at 56. So these are all just different ways of describing the data. And as Regina said, I feel like a lot of times people get data, they throw it into a computer, say, give me a regression model, give me a p-value. You've got to first actually do some basic descriptive statistics. This will allow you to understand your data and also to realize when you have errors, which pop up a lot. And if you listen to our podcast, the episode we're taping right now, it's a major error. They have the wrong, they have numbers in the table, percentages, and in the text, the numbers are different because they threw their data into a statistical model and didn't check.
If they had done basic descriptive statistics like this and really looked at it, they would have been able to save themselves a lot of embarrassment.
Yes.
So these histograms are really nice. You can see that this is symmetric. So people tend to be centered around 51, 49, around 50, and you have about the same number on either side. And that's very important when you're thinking about what is it that we're starting with and what is it that we are ending up with. So this is a histogram of the treatment group. So again, you have these bins, and each of these bins cover about 5 millimeters. And the mean here is 43. The median is also 43. So this is nicely balanced again. That fulcrum is around here. 50% of the values are below 43 millimeters, 50% are above. The standard deviation is 10. And as Kristin said, we'll talk more about that in a moment, but we can see that most of the values are about 10 millimeters away from that center in there. that Q1 and Q3, that's the first quartile and third quartile, the 25th percentile and 75th percentile. And you can see that 50% of the values fall in between the first quartile and third quartile. So we have something right here at about 35 and about 52. So you can see that half of the people are in between, 25% are below, and 25% are above.
All right, so let's talk a little bit more about standard deviation. We're going to talk about standard deviation and standard error in this lecture, and those often get confused. Standard deviation is just a measure of variability. How much spread is there to the data? How much variation is there in tumor sizes? And the standard deviation in the treatment group, we'll kind of focus on the treatment group here, it was 10 millimeters. And so just to give you a sense of what's happening, like if we look at those individual data points, remember the mean here was 43. So there's somebody at 56. That person is 13 above the mean, 13 away from the mean. There were people around 53. They were about 10 above the mean. There were people at 46. They were only 3 above the mean. There was somebody at 41 who's 2 below the mean. We have somebody at 32, they're 11 below the mean. So just kind of picking out some of the data points, you can see some people are 13 above the mean, some 14 below the mean, some only 3 or 2 away from the mean. On average, this works out to be about 10 away from the mean. So the standard deviation is giving you a sense of what's the average distance from the mean. It's not exactly the average distance from the mean because we have to do a little squaring in there, but it's kind of a rough gauge of how the average distance from the mean. It gives you a sense of the spread of the data.
Right. And the word standard deviation means that, right? What is the standard on how much each value, each patient is deviating from the mean. And this is very important because it's telling us about the variability in the population. Are people all the same? Are we starting with a control group where everyone has the same size tumor? Or are we starting with a control group where people are just all over the map? And is that what we want? Now, it's sometimes a little hard to interpret the standard deviation, but where it becomes really important is if we're comparing 2 different standard deviations. So we have this high variability one on the left with a standard deviation of 20. So you can see this extreme spread going on here, right? We have some very low values, some very high values. Compare that to standard deviation of 5 on the box plots on the right. So this is low variability. Most of the patients were about the same. Over here on the left, there was a lot of variability, a lot of difference between patients. And this is important to know when you're treating them, when you're interpreting the results.
All right, now we have a pop quiz. I think, Natalia, you're going to allow people to answer this as a poll. So which study A or study B, do you think has a higher standard deviation? This is a visual estimate that you have to look at.
Okay, so we'll wait until approximately 80% answers.
Okay. Regina, you made this one a little tricky. It's not immediately obvious.
I did. I figured, it's good to wake everyone up right in the beginning.
Right, you got to pay attention, yes.
And it also gives us something to talk through.
Yes.
Yeah, that's right.
The goal isn't to get it right. The goal is to think about it.
Yes.
Okay, so majority, 71%, answered study A, doслідження A, ending the poll and sharing results. Okay.
Yeah.
Nice job. The majority got it right. Kristin, you want to talk through this?
Sure. Yeah, I mean, this one visually, it's not. We didn't make it really obvious like the example slide we had before. But if you stare at it for a minute, you'll notice there's definitely more spread in study A. There's a little bit more clustered in study B. You've got in study A in that treatment group. There's one way out there. That outlier is really driving a bigger standard deviation. Even the control group is a little bit more spread out in study A, although again, visually, it's, you have to stare at it for a minute to see it. Yeah. Good job.
Okay, so What do we do once we have the actual results? So we have the box plot. We've looked at the groups individually. Now we need to summarize what's going on here. We have the mean tumor size in the treatment group, 43, the mean in the control group, 51. And we really want to look at the effect that our novel therapy has on the tumor size. So we subtract 43 minus 51, negative 8 millimeters. And we can also calculate the overall standard deviation if we were pooling all of the groups together.
Additional things that we want to talk about then is moving away from the descriptive statistics, which again is sort of the foundation and you need to really spend time on. Of course, eventually we want to do formal statistical comparisons, what we call statistical inference. And we want to calculate things like the standard error, the confidence interval, and the p-value. And those are the things that we really want to unpack for you today. I know you've all seen them before, but what is standard error? What is a confidence interval really? What is a p-value? So in this particular made-up hypothetical toy example, the standard error, as we'll talk about, comes out to be 5.3. The 95% confidence interval ranges from negative 19 to positive 3 millimeters. And probably a lot of you will recognize, oh, that contains 0. So it's a wide confidence interval, and this is not going to be statistically significant at the 0.05 level. And indeed, the p-value here turns out to be 0.16. Maybe that's not surprising because this is a pretty small study. So now we're going to actually unpack, what do all of those numbers mean? Where did they come from? And we're going to try to kind of go deep here.
Statistical inference, we talked about descriptive statistics, and that's where you were just describing what you have at hand. And this is so important. You cannot skip that. As Kristin said, this is where you catch a lot of errors. It's important to have your baseline. Then what we want to do is say, we realize that we just have a sample here of 20 people. And what we really want to know is how our novel therapy would fare, how would it work out in the population? So we have our initial sample, but now we need to make a guess about what it would look like in the population. And we need to do this because we only have, limited information from our samples. So we have the truth that's out there. It's not observable because we cannot recruit every single person, every single patient to be a part of the study. And this is what sometimes referred to, that you'll remember from your stats class, as a population parameter. So you don't need to worry too much about the formula. We just put that there. So if you've taken stats, it feels comfortable. So you have that truth, that population, and then we have a sample. That's the observation. And you might have heard people talking about a sample statistic. That is our guess at what the true mean is. So on the left, we have the population parameter. That's the true value, the true average improvement from our therapy. What we can actually access is our best guess at that, which is the mean in our particular sample. And we do that, we make guesses about the entire population. And this is really the heart of statistics, is making decisions under uncertainty, when the information is imperfect.
Right. And we need a way to quantify that uncertainty. And that's where the standard error comes in. And everybody's seen this before. If you've ever, read a poll, they talk about plus or minus, right? The margin of error. Well, this is directly related to the concept of standard error. So we know that because we only took a sample, we didn't measure everybody, that there's some error that arises just due to the fact that it's a random sample. And we might have by chance got a few, if we were sampling for height, a few really tall people or a few really short people, or tumors, a few really large or a few really small, just kind of by chance in our sample. So we need to quantify the uncertainty that arises just due to this sampling variability. And that is what we call standard error. And it's a measure of the amount of uncertainty in our guess. So it's that, hey, yeah, we saw an 8 millimeter difference, but hey, we're going to add to that a margin of error to reflect the fact that we didn't sample everybody. Standard error is going to be larger when there's more uncertainty, and of course, smaller when there's less uncertainty.
The word standard error, I think, is a little difficult for people because it sounds like it's something that you can fix. Like I made a mistake, like I did something wrong in my data. Standard error that we're talking about here is inherent to statistics. It's inherent to the fact that you can only take a small sample from a large population. So bad name.
Yes.
All right, let's go a little bit more depth in standard error. As Kristin said, measure of the variability of our sample statistics. So remember, we're talking here about the improvement from our novel therapy on the size of the tumor. And standard error, in addition to being a bad name, it's only a theoretical construct. It's not something that we can actually observe in the real world. And what statisticians do is ask a thought experiment. And this is actually a lot of statistics, is statisticians sitting around coming up with thought experiments to run in the head and then calculating mathematics from that. And the thought experiment they come up with is how much would the value of the statistic that improvement in tumor size, how much would that fluctuate if we could repeat that study over and over and over again with different samples of the same sample size drawn from the same population?
And, standard error is one of these concepts that really, really confuses people because it is a theoretical construct and you can't put your hands around it, right? It's this thought experiment. And I think students really struggle with that because they're saying, well, when I do a study, I get one number. How is there variability to that one number? Well, there isn't. There's variability only if we think about repeating that experiment over and over and over again, which we don't literally do. So how do we actually get standard error as something concrete? Well, there's two approaches to how we get standard error. And the one you're probably most familiar with if you've taken the stats course is the mathematical theory. And for some people like me, this is really fun. You get to do proofs. So you get to say, oh, imagine that the population has this distribution, and then we draw all these different samples and we can do some math and we can figure out mathematically what the variability of that statistic would be if, again, in theory, we could sample from the same statistic over and over again. And there's a lot of formulas that come with this that you might recognize. Now, what's interesting is that every statistic has its own formula for standard error. So if we're talking about an odds ratio, that's going to have one formula for standard error. If we're talking about a mean, that has a different formula. If we're talking about a difference in means like we are here, that has a different formula. And people often confuse standard error and think when we say standard error, we just mean standard error of the mean, which is that standard deviation divided by the square root of n. But really, every statistic has its own standard error. And there's lots of formulas that, again, you might have seen them before. We're not worrying about the formulas today. Today, we do have a difference in means problem. So that's the standard error we would be using. But a lot of teaching statistics focuses on those mathematical formulas, and I think they're very abstract unless you're, like me and for whatever reason, like proofs. So I like to actually teach, and Regina and me both like to teach with something called computer simulation, because computer simulation is much more concrete. And so we have this great amount of computing power now at our fingertips. It's funny because when Regina and I were getting our PhDs, it was a very different landscape. And, for one of my papers, I was running simulations and I would literally have to write the code and press go on it and then leave the office and wait till the next morning to see if that simulation had gone right. And sometimes it didn't. And then I'd start the whole process over because it would take 24 hours to run these simulations. You can run those same simulations now in a fraction of a second on any given laptop or probably your phone at this point. So we have huge computing power, which means we can virtually run experiments. So what we do is we set up in the computer a virtual world and we say, hey, we have this radiosensitizer and we have this placebo and we're going to imagine that there's some effect or that there's no effect. We can put in different assumptions. And then we can sample from the population, a bunch of different patients from the placebo, a bunch of different patients from the radiosensitizer group. We literally sample over and over again, and we keep calculating that difference in the tumor size over and over and over and over again. And we can see how much does that statistic vary from sample to sample. And guess what? You don't have to do a whit of math to do this, and you can get the right answer.
Kristin, how about you take the simulation?
Okay, I'll walk everybody through the simulation that I set up in the computer. So I made a simulation that kind of mimics this hypothetical toy trial example. And my first thing I'm going to do is say, let's imagine we have just sort of an infinite population of treated and control patients, and I have to put some parameters to that. So let's say the mean tumor size in both groups is 50. So I'm going to start by simulating the situation where the treatment does not work. We can do it both ways, but I'm saying, well, what if the treatment doesn't work? The standard deviation is 10, tumor size is 50, and I'm going to assume normal distributions. And then those are two distributions, so I can randomly select, the computer can randomly select 10 values from each of those distributions, 10 treated and 10 control. Just because they come from the same distribution doesn't mean I'm going to get the same mean value for each group at the same time. So maybe one time I get 43 for the control group and 42 for the treatment group. The next time I get 50 for the control group and 60 for the treatment group. In each one of those virtual trials, I calculate that statistic of interest, which here is the difference in the tumor sizes, the difference in the means between the groups. And then I can do this as many times as my computer will allow. I ran these 100,000 times because I can do that in a fraction of a second in my computer. It doesn't matter how many times you run it. I just want a large number so I can literally see that fluctuation. And then I'm going to plot it, observe it, and see, oh, how big is that difference? How big is that fluctuation?
And here are the results of our first 10 of these made up thought experiment virtual trials that Kristin did. And the values are on the left, but of course, Kristin and I love to visualize things. So we have them as a little bit of a plot on the right. What we see here, that x-axis is the difference in the means. That's the value we're seeing on the left. That's the thing Kristin said. We're taking, we're sampling from the treatment group, the control group. We're finding the mean, and we're taking the difference between the means. We have these 10 dots, and we have the first simulation up at the top, the second here, the third, fourth, fifth, and so on. And what you can notice, and they are bouncing around this middle value because remember, Kristin said, here we are assuming there is no difference between the two groups, that our novel therapy does absolutely nothing. Is it always zero? No, because this is the uncertainty that comes when we're only sampling 10 people from each population. So sometimes it's an improvement over here on the left. Sometimes it actually made things worse over here on the right. Now, the standard error is a measure of that uncertainty. So it's talking about how much do these values, these dots, how much do they fluctuate around the mean, around this mean of 0?
So that was just showing you 10 trials, but then we did this 100,000 times. And rather than show you 100,000 dots, I put it together in a nice little histogram. And you'll notice it forms a beautiful normal curve that happens when you run large numbers of trials like this. Statistics in the long run tend to be normally distributed like this. So if I ran 100,000 virtual trials, what you'll notice is, yeah, I get right around 0 a lot. Good. I ran my code well. If I didn't get around 0, there'd be a problem because I know that I assumed that there was no difference. But there is some amount of fluctuation. So sometimes, as Regina said, the treatment group did better. Those are the negative numbers. Sometimes the control group did better. Those are the positive numbers. And we can look at this normal curve and say, well, what's the standard deviation of these statistics? So the standard deviation of these statistics, I can calculate. I take my 100,000 values for the difference in means. I calculate a standard deviation in the way we normally do. And that turns out here to be 4.5. So the standard deviation of the differences in means, the standard deviation of a statistic, that gets a special name. So standard error is literally the standard deviation of a statistic. So when we talk about this theoretical variability of a statistic, we're talking about the standard deviation in this hypothetical world of this statistic, and it gets its own special name, which is standard error. So that's what standard error is. It's a special case of standard deviation when we're imagining what could happen if we were repeating trials over and over again. Now, it came out to be 4.5 here. Notice I didn't have to do any math. I just ran this in the computer. I could know nothing about math. I get a value of 4.5. But if I happen to also know that somebody else has proven the mathematical formula for figuring this out, and I plug into that formula, which just involves the standard deviation squared divided by the sample size, it also comes out to be 4.5. Again, that's a good check that I did my code right because my simulation matches the math. And this is a really great trick. Actually, I'm teaching my students this. If you ever have to solve a mathematical problem, just go in the computer, simulate it, get the right answer. It's like having the answer from the back of the book, and then you can work backwards the math.
Again, I should stress that you will not need to do this sort of formula by hand. This is to unpack what's happening. We want you to see this. Maybe you learned it in some stats classes before, but now that we have computers and statistical software.
Regina, I should also add that you're not going to need to do these simulations either.
True.
We are showing these just for illustration. You will put your data into a computer program that will calculate the standard error for you, but we want to show you what's happening, what it actually means underneath the hood. Yeah.
It's just like learning how to drive. You're a better driver if you know a little bit about what goes on under the hood. You don't need to be a mechanic and know how to fix your car or build a car, but it's nice to just know what's going on in there. So this is what we were doing when we were sampling 10 people from looking at 10 people, running an experiment on 10 people. What happens if we increase that now to 50 people? We randomly select 50 treated and 50 control patients in here. What would we expect that difference to look like?
I love this picture, Regina, because you can just see the shrinking. The dots are all of a sudden clustered way closer to zero. And this is the beautiful thing about statistics. If we sample more people, we have much less uncertainty. We get much closer to the true value. So our standard error now is way, way smaller. How much those dots are bouncing around the line, you can see visually is way smaller. And that makes intuitive sense because 50 per group is a lot more than 10 per group.
We have less uncertainty. So we're going to have a smaller standard error. So just to put them side by side, we've got our 10 per group and bouncing all over the place. It's just bouncing a little less when we have 50 per group. If we had 100,000 per group, we would have even less uncertainty and it would bounce around less. But it's still going to bounce around because that's what samples do. So are we ready for pop quiz number 2? Which study has a bigger sample size, study A or study B? Did I make this one a little easier?
Well, you're asking which has the bigger sample size, so they have to be careful. You're not asking which has the bigger standard error, but which has the bigger sample size.
Bigger sample size. Which study had more people in it?
Yeah.
So remember, if we have more people, we have less uncertainty, which means we have a smaller standard error. We're going to have less bouncing around.
Okay, I'm ending the poll, sharing results. So majority answered B, but it actually should be A.
That's right, yes.
8 people said A, 9 said B, right? Answer is A. Kristin, you want to walk through why that is?
Sure. Yeah. I mean, so this is a little bit tricky because we weren't asking for the bigger standard error, which would be B. We're asking for the bigger sample size. So you have to step back 2 steps and think about, okay, in study B, we have a lot of uncertainty. A lot of the standard error is large. Remember, smaller samples give us greater uncertainty. Bigger samples give us less uncertainty. So it's actually study A that has the bigger sample, which leads to the smaller standard error.
It was a bit tricky.
It was a bit tricky, yes.
It was tricky. Again, we want to make sure everyone's awake and paying attention.
Regina, I wish I'd had that question. I'm giving a final on Friday. I just sent it to the printer, though, and that's a good one. I should have put that on my final. A little tricky.
You have to connect the dots. You have to
Yep.
think it through, which is a sign of advanced thinking.
Yes.
There you go. So here is what we have for the 100,000 results. Again, our sampling and distribution. Here, when we're doing it for the bigger sample size, now the standard deviation is only 2. So the standard error is smaller. And as Kristin had pointed out, we can do this mathematically. So we had a smaller standard error for our bigger sample size.
Right. So bigger sample size leads to smaller standard error. There's another value in here that actually also influences the standard error, and that is our standard deviation. How much variability is there in tumor size in our patient population? Some patient populations might be more variable, some are less variable. Remember, in my original simulation, I assumed a standard deviation of 10. These are totally made up numbers, by the way, just for illustration. But what if it was bigger? What if the standard deviation in tumor size was 20 instead of 10? So I ran the same simulation. I'm back to 10 per group, by the way, going back to the original sample size. I'm just changing the standard deviation. I'm doubling it. So what do you notice happens here, Regina?
Well, what we need to do is look at that width. So we needed to have been paying attention to what's going on on this horizontal axis down here. So if we're going to have more variability, we can just think this through. If we have more variability in the population, we're going to have more uncertainty. And more uncertainty means bigger standard error. So we're going to have more spread in the results here. And sure enough, standard deviation here is almost 8.94. Compared to, what was it, 4.5?
Yeah, it's basically double, because we doubled the standard deviation. That actually doubles the standard error in this case.
That's true. That one works. It doesn't work that well.
Doesn't always work, but yes, in this case.
With a sample size. Okay, so our standard error is bigger. And again, we can check it mathematically if we want. And yes, it comes out perfectly. Pop quiz. Okay. Now everyone is on their toes, right? Which study has bigger variability in tumor sizes? So bigger variability means bigger standard deviation. What will a bigger variability do to your uncertainty? You can try thinking it through that way, even if you don't want to look at the beautiful histograms.
Let's wait for a few more answers. I think we are on the right track. I'm ending the poll and sharing results. So majority answered B.
There we go. Good job, guys. Everyone is paying attention. So we have the bigger standard error over here because we had a bigger variability. That standard deviation is bigger here. Bigger variability, bigger standard deviation, more uncertainty, bigger standard error.
So these simulations illustrate for you the things that affect standard error. And I think these are very intuitive. If you have a smaller sample size, more uncertainty in your guess, so standard error is bigger. If the thing you're measuring has more, it bounces around more, it's more variable, bigger spread, that's also going to add uncertainty, and that's also going to increase the standard error.
All right, now we're going on to the next step of what we said we were going to unpack. We finished standard error. Now we're going to move on to confidence intervals. And this is perfect because it actually uses standard error, which we all understand now after 3 pop quiz questions. The goal here is to realize that, again, we only have a sample from an entire population. And we estimated, for example, here that our improvement in tumor size was 8 millimeters, that our difference in the means between the two groups was -8. But we also realized that this is just one value from the 10 people, the 20 people that we sampled. And if we were to sample more people, it's going to bounce around. So we need that margin of error, kind of putting a net over our effect size, our guess of the effect size, to say what we think it is in the population.
And if we want to be really precise about what a confidence interval means, here's the precise definition. So again, this idea of repeated experiments, if we could repeat the experiment over and over again, we want to build our confidence interval, say our 95% confidence interval, that's the most common. A 95% confidence interval should include the true value 95% of the time, but we are allowing that when we repeat experiments over and over again, we can miss it 5% of the time. We have a 5% miss rate. I just put this link in. If you can Google and find Christopher Magnuson. If you want to actually see kind of a real-time simulation like these simulations we've been talking about today of how confidence intervals work, it's a beautiful little app that I love to send students to because it'll show you it's going to run a whole bunch of virtual trials and you're going to see there's one true value and the confidence intervals, most of them contain the true value, and then every now and then about 1 in 20 times you miss the true value. So it's a nifty little app.
It's a great app. It's a little like a video game because you can say, okay, what happens if I change the sample size? What happens if I change the standard deviation, and see the effects that way? So I love it. It's a lot of fun to play with. Okay, now we need to figure out how to calculate it. Again, your statistical software will do this, but we need to see what's going on underneath the hood. And there are 3 parts to a confidence interval. The first is going to be that point estimate that we talked about. That is going to be the mean or the difference in your means or odds ratios. That's the thing that we're most interested in. What is the effect of our medication? And then we are going to we want to have this net around it, this margin of error, and we want it on both sides. So that's why we're going to have this plus and minus. We're going to add and subtract something to that, and 2 things. We're going to multiply them together. Now let's jump to the last one, the standard error. That is exactly what we just talked about, how we calculate it there. It's a measure of the variability of the statistic. It's talking about how much uncertainty is in our point estimate. And then we're multiplying that by it's like a buffer or a fudge factor or inflation factor. So how many standard errors, how certain do we want to be? Now, 95% confidence is pretty standard in scientific and medical literature, and that translates to, and Kristin will talk about that in a moment, to a multiplier of 2. And if you want to be more confident, you are going to take it out a little further because we want to make sure that we capture everything. So you just multiply that 2, okay, it's about 2 for 95% confidence by standard error, and then add and subtract it around the point estimate.
Yeah, and let's talk a little bit about where that 2 comes from. So notice that when I showed you the results of the simulation, it made this beautiful normal curve. So lots of times our statistics, if we think about what would happen if we could repeat the experiment over and over again, turns out that they follow this nice normal distribution. That's why we love normal distributions in statistics. And if your statistic indeed follows a normal distribution, then you can determine this level of confidence. It just comes, that number 2 comes from a normal curve. And so technically 95%, it's a value of 1.96 to the right and left of the mean. But we often just say 2 because close enough. But technically it's precisely 1.96.
What we were working on here was not quite that normal distribution. What we're working with here is something slightly different. It's called a t-distribution. And we're only doing this because we had a very small sample. We had 10 in each group. And as we've talked about before, it's we have to pay a penalty. We have to pay a price for the fact that we just have so much uncertainty. We have limited information. So a t-distribution is very much like a normal distribution, just a little flatter, just a little lower, a little bit more in the tails. So the multiplier for the 95% confidence interval is still somewhere around 2. It's just a little more, 2.1. So we're just taking our standard errors out 2.1 times instead of 1.96 times.
All right. So that hypothetical, that one trial that, how would we, or how do we calculate 95% confidence intervals from all of those virtual trials in our sample? We can, in each sample, take the difference in means of the tumor sizes, and we do plus or minus 2.1. Again, the little bit of extra on the 2 just comes from the fact that we have a very small sample, and we multiply it by the standard error, which we have to estimate from each sample. We don't know it ahead of time.
Kristin, go ahead and talk through this one because
okay, sure, yeah. So I just took out of my simulations. I'm showing you the first 20 just because it's easier to show just 20 in a full plot. And I'm showing you that in each virtual trial, I did that formula. I calculated the confidence interval, and you'll notice that because remember, in my simulation, there's no effect for the radio sensitizer. It doesn't work. Sorry. The true mean is 0. And what you'll notice is that the confidence intervals almost always contain 0. But one time out of 20, which is what a 95% confidence interval is supposed to do, the one that turned red there, I missed it. I missed the 0. Now, the thing is, when you run a study, you don't know if you're on the red one or on the blue one. There's no way for you to ever know. You either hit it or you didn't. But we build confidence intervals in a way so that in the long run, we're hitting it 95% of the time and we're missing it, 5% of the time.
Now, how would we calculate this in real life? If we wanted to do it the old-fashioned way, we would have that point estimate just to show you where that confidence interval came from. We have -8 millimeters. That's our point estimate. We have our t-value, that multiplier, 2.1. And then we would calculate the standard error for this and for what we actually observed in our sample. And you don't need to worry about the formulas here. This is just if you wanted things from stats class. And we calculate it to be 5.3 millimeters. So all we do is multiply 2.1, 5.3, add and subtract it -8. And that is where we're getting the confidence interval that we showed you earlier, -19 millimeters to 3 millimeters.
Right. So this is for our one actual trial that we're imagining we actually ran in real life, not the simulated trials. And how do we interpret that, right? So now we get this 95% confidence interval, -19 to +3. And so what's the way we interpret it? We can say things like effects anywhere from a 19 millimeter improvement to a 3 millimeter worsening. That's the positive is the control group did better. They're all plausible at the 95% confidence level, all plausible values. We also know from looking at the confidence interval, wow, it's wide. Our estimate of the effect is imprecise. It's a little clue that, maybe our sample was too small. Or that we had a lot of variability in tumor size, right? The confidence interval also tells us something about hypothesis tests and p-values, which is what we're going to talk about here in a minute. So just to know, there's a one-to-one correspondence between confidence intervals and p-values. So we know by looking at this, since the confidence interval contains 0, we know that this is not going to be significant at the 0.05 level because it's a 95% confidence interval. Now, you don't only have to use null values of 0. We tend to use our null value for many times when we're calculating p-values. We start with a null hypothesis. There's no difference. You don't have to do that. Your null hypothesis could be that there's a difference, no bigger than 2 or, smaller than 2. So there are other hypothesis tests that are also buried in here that you would be able to get out of without actually having to calculate p-values if you wanted to.
So let's go on to p-values then. Here, our goal is to, a little like what we've been doing so far, we need to quantify this uncertainty. And the overall goal with p-values and hypothesis testing is to help us distinguish what is a real effect that we observed from what is just a chance fluctuation. Because as we've been talking about so far, we've seen in our simulations, results bounce around. So it can look like there's something real there, but it's just something from random chance. So p-values and hypothesis testing helps us stop from fooling ourselves.
Right. And so the precise definition of a p-value, it's the probability of the observed outcome. So in our one trial that we, imagine that we did, we got a difference between the groups of 8 millimeters. So it's that -8 millimeters. It's the probability we would have seen -8 millimeters and all more extreme outcomes. So -8 millimeters or a bigger difference between the groups. It's the probability that we would have observed that if the null hypothesis is true. And remember, I built into my simulation no difference between the groups. So if my simulation is correct, what's the chance I would have seen an 8 millimeter difference between the groups or anything bigger than that, anything more extreme? That is what a p-value gets at.
And how do we calculate a p-value? Again, if we wanted to do it by hand, first we calculate what is called a test statistic. And this is where some of you might have nightmares from statistics class. A t-statistic, it's really not so bad. It's just a ratio here. It's kind of like a signal to noise ratio. So let's break it down bit by bit. We have observed value. So this is the value of the statistic that we actually observed here. Again, the mean or the difference in mean or the odds ratio. For ours, it was the difference in means. And then we see how far that is. Ours was -8. How far is that from this null hypothesized value that we're testing? And the null value is the thing we want to disprove in a way. We want to show that it's not zero, that the mean difference is not zero, that it's not true that the therapy has no effect. And so that is going to be zero here. So at the top, we have how big is our observed difference from nothing. And at the bottom, we need to scale this by our standard error. Again, this pops up over and over. This is the theme. We need to talk about how much we would expect our sample statistic to vary from trial to trial. And we just do all of that. So walk us through quickly, Kristin.
Right. So formally, we start with our null hypothesis. Here, we're going to say the null is that there's no effect. We often choose no effect as the null. Again, you don't have to. So that effect size being 0. We, in our one trial, observed this value of -8. We already talked about how the estimated standard error from our sample here is 5.3. And so we do -8 minus 0. That tells us, hey, how far is -8 from the null value? And then we divide that by the standard error. The standard error is like the background noise. And we want the distance between the observed value and our null to be so big that it exceeds the background noise. Here we get a value for our t-statistic of -1.5, which actually it's saying, hey, we don't exceed the noise by all that much. It's a little bit more than exceeding the noise by just the average amount, but not by much. And that translates to a p-value of 0.16, which everybody knows is not an impressive p-value. It's
not an impressive p-value.
So how do we interpret that p-value? Sorry. It's 16%. And we would say if the treatment does nothing at all, then the probability of getting an effect as big or bigger than the one we observed is big or bigger than -8. So -8 or 9 difference between the group, or 10 difference, or 11 or bigger between the groups. With that value, that probability is 16%. In other words, hey, it's not that unlikely, right? We could have gotten a difference this big just by chance if the null is true. It's not inconsistent with the null.
Do you want to walk through this? Or do you want me to?
Yeah, this is just from the same simulation that I ran above. Instead of me showing the millimeters of tumor at the bottom, I just took each of those virtual trials and I calculated a t-statistic like I just did for our one observed trial, right? So I calculated a t-statistic out of all these simulated trials to say, how often do I get -1.5? Intuitively, we can kind of understand if I'm 1.5 above the background noise, that's not much. And what we see is that actually it was pretty easy to get a t-statistic of 1.5. When I assumed no difference between the groups, I got values of 1.5 or greater, or -1.5 or less, 16% of the time. And this is what we call a two-sided p-value. It's pretty easy to get differences of 8 or bigger just because there's a lot of variability here. We sampled a really small sample. And two-sided p-value just means we look at the possibility that, hey, it could have gone the other direction. The radiosensitizer could make things worse. So we always say, when we say more extreme, we almost always mean in both tails. So that's why we get the value of it's 8% in each tail. The two-sided p-value is 16%.
And in clinical trials, it's usually two-tailed.
Almost always we want to go two-tailed because we don't want to assume that it's impossible that the radiosensitizer could make things worse, right? Because there are cases we know where treatments actually make things worse. So we don't want to go in assuming that it can only improve the tumor because it could do the opposite.
It's more conservative to do two-sided to make sure that we're protecting ourselves against both. So just to talk about our hypothesis test again, our null hypothesis is generally that the treatment does not affect tumor size, and the effect is 0. Then we need to come up with what is called an alternative hypothesis. And that is usually the opposite of the null hypothesis, that the treatment does affect tumor size and that the effect is something that is not 0, not equal to 0. Then we need to choose our alpha, or our significance level, or p-value threshold. Again, it's standard in the literature to choose 5%, 0.05. You can choose other things, but you need to have a good reason for doing so, especially if you are going to make your threshold less stringent. And then you compare that to the p-value that you observed, 16%. And you say, 16% is bigger than 5%. And we cannot reject the null hypothesis. If it's smaller than 5%, we can go ahead and say, yes, it looks like we can reject the null hypothesis. Here, we cannot reject it. We don't have evidence that this treatment actually does affect tumor size. That's the formal hypothesis test.
Yeah. Now, what's interesting here is let's talk a little bit about what that significance level means. So we have to set this, what we call alpha or significance level. It's typically kind of by default in the literature set at 0.05, mainly for historical reasons. And so what I did here is I'm using that same simulation, 100,000 virtual trials, where I know there's no difference between the groups. And what's interesting is I went in each virtual trial, I ran a t-test, I calculated a p-value. So I've got 100,000 p-values from 100,000 virtual trials. And what you notice is if I plot those p-values in a histogram, they have to range between 0 and 1 because of the probability. It follows what we call a uniform distribution. It's equally likely if their treatment really does nothing, it's random, right? So it's equally likely I'll get anything between 0 and 1. And so what's interesting here is that it's actually expected that sometimes you're going to get p-values less than 0.05 purely by chance when the treatment actually does nothing. It would be weird if I did this histogram and I was missing the bar from 0 to 0.05. Significant p-values are going to arise by chance. If we set our alpha at 0.05, what we're essentially saying is we are allowing that if the treatment does nothing, we are still going to reject the null hypothesis incorrectly. In other words, get false positives 5% of the time. We call these type 1 errors. This is false positives. So we are allowing our type 1 error rate to be 5%, meaning even when our treatment does nothing, 5% of the time, I'm going to get a significant p-value anyway. I'm going to make some false positives.
As Kristin talked about, it's almost default to use an alpha of 0.05. And for historical reasons, it was chosen to be this way. But there is nothing magical about 0.05. I assure you, nothing at all magical. And Kristin and I talk about this in our podcast episode on p-values and the weirdness that happens when we do this. And especially because it turns out mathematically, statistically, that 5%, the 0.05, is actually a fairly weak level of evidence. So it's a little unfortunate that we've chosen 0.05 as our standard default for historical reasons, but 0.05 is not the only possible choice. You can make it more stringent. You can make it 0.01 if you want.
Yeah, I'm going to put another plug in for that p-value episode of Normal Curves, Regina, because if you really want to, we talk a lot about the history and why it's 0.05 and what that means. So if you really want to understand that in even more depth, go to that episode. P-values have strengths and limitations. I think there's a whole movement of let's ban p-values and get rid of them. The problem is p-values have one job that they're good at, and they've been used for more things than they're supposed to. So the thing that's good about p-values, how it helps us, is it helps us to not fool ourselves. So go back to that example that I used at the beginning, this 8 millimeter difference. You might look at that and go, oh, wow, that's really helping my patients. But when we calculate the p-value, it reminds us that, oh, wait, an 8 millimeter difference could have arisen just easily by chance, even if the treatment did nothing. So it keeps us in check from being overly confident.
There are also so many misinterpretations of p-values, and the article I wrote for Nature talks about some of these. There are so many. We're just going to list a few here, and some of it comes down to the way it's written in English. So it may not translate perfectly, but hopefully you can still get a little bit of the idea behind what's going on here. The p-value is not the probability that your result arose due to chance. Remember, the p-value is calculated when we assume that everything is due to chance, and then we look to see how extreme our value is. So we cannot talk about the probability that your result is just random chance. We can't talk about the p-value being the probability that your result is a false positive or that it's wrong. We can't talk about the p-value being the probability that the null hypothesis is true. It doesn't mean that there's a 5% chance that your finding is a false positive. We can't use the p-value for any of this. It's very limited and strict in what we actually can use. So the only thing that we can say about a p-value is this very convoluted, very strict, very restrained definition that Kristin mentioned before. The probability of the observed outcome and all the more extreme outcomes if the null hypothesis is true. So we cannot talk about the probability that the null is true. We're just not able to do that in our statistics framework. Again, tune into the episode for a little bit more about why.
It's about the probability of our data, not the probability of the null. And that's where it gets confusing. It's really the probability of our data, not the probability of the null, because we assumed the null is true. So that's where people get confused.
But very, very subtle in there.
So for the cancer study, again, we got that p-value of 16%. We would not say, therefore, oh, that means there's a 16% chance that the treatment doesn't work, and therefore an 84% chance that it works. That's way overly optimistic. We cannot say that. That's not what a p-value means. Yeah.
Okay, pop quiz number 4, true or false? A study reports a significant improvement in survival for new therapy with p is 0.01, and it's for a standard null hypothesis of no change in survival. The poll is on top. Okay, true or false? This means that there is only a 1% chance that this is a false positive and a 99% chance that this new therapy truly improves survival. I made the poll window go away, so I can't see.
Oh, that's okay.
Are people answering?
So yeah, they are answering. They're approximately 63%, 68%. Let's wait for a little bit more answers. Okay, I will stop the poll and share result. So majority answered false.
Good job. Good job. Oops.
Okay.
The only correct interpretation is that if the therapy has no effect, there is a 1% chance of seeing results at least as extreme as what we observed. We can't say anything about the probability that this therapy truly improves survival. It's very sad. We want it to be about that, but that is not what p-values are. Very sad. Mm-hmm.
So as we've sort of alluded to, p-values have lots of limitations because they depend on a couple of different components. The effect size is in there, the variability of the outcome, the sample size. And so any one of those can drive a large or small p-value. So for example, if you have a really, really huge sample size, that's going to make your standard error so small that your p-values are going to be really small too, because you have extreme precision. And it turns out in huge samples, p-values are kind of irrelevant. You can detect the tiniest differences between groups that have no clinical meaning. Also, of course, a p-value doesn't tell you anything about the quality of a study. So it has this very, very small job it does. It helps us distinguish random noise from real effects, and that's it. And you can't put more on it than that. bottom line, can't interpret p-values in isolation.
I'm not going to read this entire thing, but the American Statistical Association actually came out with a full statement on p-values because they realized people were just misunderstanding them, misinterpreting them, abusing them. So it's actually a very interesting read, and you can understand it even not being a statistician. So I encourage you to go look that up. The bottom line, though, is that a p-value is just one of many tools that we have in our statistical toolkit. Just like you have a great screwdriver, you don't want to use it as a hammer. It's not very good for pounding in nails. It's good for screwing screws. It does that one specific job very well when used correctly, but that is it. Don't try to make it out to be something.
And I'll add, Regina was involved in this statement on p-values. I believe that you were the person leading the discussion, and boy, that's an interesting story. And again, we'll plug that p-value episode.
That
cats,
was
I believe you
fun.
described.
That was fun. That was fun. Yes, the statisticians.
All right. So the last concept we wanted to cover today, which is related to everything we've been talking about, is statistical power. Statistical power is the probability that if you do a study, that you're going to correctly reject the null hypothesis when you should. In other words, it's the chance of detecting a real effect. I like to think of it a little bit like sensitivity in diagnostic testing. If there's a disease there, if there's an effect there, you're going to catch it. So it's kind of the sensitivity of your study.
Now, statistical power is very strange, and the best way to understand it is through these thought experiments again. So what if the null is false? What if there is a true effect here? Let's assume that the true effect is -5 millimeters, that it actually helps that you get an improvement of 5. Again, this is just a thought experiment, so we're just choosing this one at random. Let's assume we're going to do our simulations again, and here we're going to assume that the mean tumor size in controls is 50, and in treated, it's 45. And everything else, we're going to be doing the same. So we're going to select our patient. We're going to calculate the p-value from the test. We're going to repeat this 100,000 times, and we're going to look at the distribution of p-values. And this is going to give us information about statistical power.
So here is the distribution of p-values. Remember before, when we started with that original simulation where I assumed no difference between the groups, the p-values followed this nice uniform distribution. It was equally likely if the treatment doesn't work, I'd get a p-value anywhere from 0 to 1. Now we've built into our simulation, actually the treatment works. It has a small effect, -5 millimeters. So what we see is, this is good, that a lot of times in our studies, we actually found a significant effect. Now it was only 18% of the time because this is such a small trial, but that blue bar represents all the times that we got a significant result. So when I run 100,000 studies, yes, some of the time I get a significant result because there's really a true effect there. The sensitivity here is 18%, but a lot of times I missed it. I got a big p-value simply because there's a very small sample, so our standard error is large. So even though there's something there to detect, we missed it in most of the trials. This is an underpowered study.
We like to have a power of 80% or more. So this is a very underpowered study. And we can look at that by flipping that information around in a different way. So what we have here is statistical power is on that vertical axis. So remember I said we like to have about 80% power. That's where we have this horizontal line, and it goes from 0 to 100, and we had about 18 before, so we were somewhere around here. Now what we have on the x-axis, and with each of these dots, is saying, okay, let's take that imaginary idea we're talking about, that effect size of -5 millimeters. Let's try expanding this out and say what the true effect size is in all these different scenarios. And we can say then that we only had 10 people in each group. And if we had, let's say, a 13 true millimeter difference. If it was a big difference in the population, this is really what it would do. Then we would have 80% power. But if we were down here at small differences of just, 5 millimeters, 10, 15 over here, it's, well, there we go, over here, 10, here's 10, 5, 10. We still have very, very low power.
I don't actually know if 13 is unrealistic, Regina.
Oh, okay. Yes, true.
Yes.
We don't know. Wait.
Yes. I had made some slides before about sports medicine where I knew the clinical. So I'll leave that for the oncologist to decide.
Mm-hmm. Yes. Uh-huh.
But this is called a power curve, and we love power curves because it's a really good idea before you design a study, while you're designing it, to draw the power curve so you have a sense of like, how big of an effect do I really have adequate power to detect? And if it is unrealistic, I probably need to sample more.
And 13 can be realistic in oncology.
Okay, yeah, I was wondering about that.
Okay.
Yes, there are big tumors.
These slides came originally, again, from a sports medicine example where I had an unrealistic slide in there, but I don't know for oncology. Yes.
Yeah, it works also.
Good. So
now there's another way we can look at statistical power, and go ahead, you take this one.
Oh yeah, either one. So that there's two ways to do these power curves. You can say, hey, I have a fixed sample size and I want to see, hey, how big does that effect have to be that I really have a good chance of detecting it? You can flop it the other way and say, well, if I pick a fixed effect size, what sample size do I need to detect it? So often when we're doing sample size calculations, we might start with what we think is a realistic or clinically meaningful effect size and draw this power curve to help us determine the sample size we want. So we just flipped it on the x-axis here. We have the sample size per group. The y-axis is statistical power. And I ran my simulation assuming, hey, the effect size in every case is -10. So how big of a sample do I need if I think 10 is realistic or clinically meaningful? And it turns out somewhere around 15, 16 per group. So that's how you can do a sample size calculation. How do you pick that effect size? Often it's like, what's the sort of the smallest clinically meaningful effect that I want to be able to detect?
Pop quiz number 5, true or false? This one is a tough one. If we increase our sample size from 10, n equals 10, to n equals 15, we gain more statistical power than if we were to start with a sample size of 40 and try to increase it to 45. So to go from 10 to 15, that increase in power is bigger than our increase in power if we were to go from 40 to 45. So here we really want to look at the graph, and we want to look at 10 and 15, and we want to look at the power that's coming from that. And then we want to look at N of 40 and N of 45 and look at the power that's coming there.
Okay, almost there, 61%. A little bit more answers, please. Okay, I'm ending the poll and sharing results. So majority, 70% almost answered A.
Good job. I'm very impressed because this was a difficult one in here. The idea is that when we have very small sample sizes, any tiny little increase in sample size, bringing more people in, is going to give us the most bang for our buck. It's going to give us the most increase in statistical power. If we already have something that's pretty sufficient up here over 80% power, if we're going from 40 to 45, it's not changing it all that much. It's good to have, but what's really important is not to have very small sample sizes. And it's worth putting your money in to make sure that you have something that's at least adequate. Anything to add there, Kristin?
No, that's great explanation, Regina. Yeah, it's diminishing returns. Yes, a lot of things in statistics. Diminishing returns.
Yes.
We want to point out some further resources. So Regina and I do several online courses together. We do one on clinical trials, how to run, how to design, how to analyze a clinical trial. We have one on statistics that's really meant to be user-friendly. Not as user-friendly as the podcast, but almost, called Demystifying Data, really to give you an introduction if you are somebody who is allergic to statistics or afraid of statistics. I also teach a whole certificate program online called the Medical Statistics Certificate Program. It gives a much deeper dive if you really want to go deep. It's a good idea to sequence those if you're afraid of statistics and start with the gentler one first. And then I think we have a few other resources on the next slide, Regina. So we've been co-writing a column or switching off writing a statistics column for the journal PM&R. And we have a lot of topics covered by now. We've been doing it for like 15 years. So, if you want to learn about linear regression or logistic regression, principal components analysis, histograms, box plots, we have like one-off power,
statistical power, p-values.
We have lots of columns in there trying to go deep, but written in a way we both have journalistic backgrounds, so written in a way that we hope clinicians can understand. And then, of course, the podcast we think is a lot of fun.
That is it.
Oh, amazing. What an amazing lecture. You were such a powerful duo and was a big, I would say like very, very small or big power, but small p-value. I cannot say that.
That's great.
You just multiply each other and enhance. It's just incredible. I like how you bounce slides from one to another. It's a great
in the podcast
synergy.
we talk more about boys and stuff, so it's more fun.
Kristin and I have been friends since grad school at Stanford many years ago. Yes.
And amazing slides, and thank you so much for so much work put into them. They're very thorough and explain the concepts very well. Thank you. Bravo. I am very impressed. Thank you. So I'd like to open the floor for questions. If you have any questions, please, you can turn on your mics, cameras. If you have light, you can ask questions.
Put something in chat.
Yeah, put something in the chat. Yeah, we see a lot of hearts and bravos. Thank you. It was a really well done lecture. Good job. So few of our teams actually studying clinical trials. So they are going through the process of writing a clinical trial and calculating sample sizes, what the sample size they need. Is there any easy tools that they can also use online?
This is a great question. I don't know how much access you guys have especially with computing power in it to AI right now. But
yeah, they do have access to AI.
But, so there are plenty of online sample size calculators where you can go and plug in a few numbers and it'll give you some general idea. The optimal way to do sample size calculations is through a simulation, which if you didn't code in R before, it's like, how would I do that myself? Now the AI will write a simulation for you in R. So if you know a little bit of, just a teeny bit of R and a teeny bit of how to use AI, you can do some pretty sophisticated sample size calculations on your own. And of course, there are online calculators as well, but I love doing them by simulation because you can get a little bit more sophisticated.
ChatGPT and Claude are both good.
Yes.
But when I tried ChatGPT for just simple descriptive statistics, it was not very accurate. I'm not sure if I was using it correctly.
That is a great point. So you have to be a little careful with these AIs. They can do some very sophisticated things, and sometimes they will go wrong on like adding two numbers. So it's kind of amazing, and I don't quite understand it because it has to do with the language model, that it can really go wrong on simple numbers. So I'm teaching this to my class right now, is how to use AI in combination with understanding the statistics and some coding. And it's interesting. You have to double check and be careful, but it can do some very sophisticated coding, and it's great for data visualization, which as we talked about at the beginning, Regina and I think a lot of people just throw their numbers into a computer program, never visualize their data. There was a barrier before because writing code to make a graph actually really complicated. I've had my undergraduates now doing 10 different graphs of the same data set, as fancy as can be, all using AI. So if you haven't tried AI for coding, it's really, really good now and getting better.
Yeah, impressive. But let's say if they start with something simple like a spreadsheet, they can do descriptive statistics in the Excel spreadsheets. And one question I have, like T distributions, how would they know? First, they need to start with plotting the distribution, right? If they start analyzing the data to see what distribution it is.
The statistical software will actually often, most of the time, get it right. So if you go in and say, I would like to do a t-test, which is what we did here, that was that signal to noise, it will do that. I think in Excel, it's t.test, and then you give it the columns with the data, and it will do that automatically. What we were doing was unpacking a little bit so you could see what's going on behind the scenes. But
let's say if you want to test your data, if your statistical software spits it out correctly, just to validate, right, the results, you would the first step would be just to plot the distribution to see how it looks like. Right?
Yes, a histogram. So again, yes, histograms. You could do histograms in both Google Sheets and in Excel.
You don't need your underlying data to be normally or t-distributed, though, in order to run a t-test. It's the statistic that follows that t-distribution. So there are some checks that you want to run on your data to make sure that it's not too skewed if you have a small sample and you want to run a t-test. But in general, you don't have to, the underlying data themselves don't have to follow a t-distribution.
What if the data is not normally distributed and there's big skew, then what happens? That's another topic for discussion.
It depends on how big your sample is. So if you have a large sample, notice how the statistics, when we did those simulations, even with 10 per group, the statistic came out nice and normally distributed. So it turns out that if you have a large enough sample, it doesn't really matter if your underlying data are not normally distributed. When you have a small sample, though, you do have to worry about the fact that the data are skewed, and you want to use often what's called non-parametric tests,
right?
Which we talked about in our episode on hookworm therapy.
Oh, I see. We did. Whitney test, right?
Yes, tests like those that are based on ranks of the data. Yeah,
I see.
So I put into the chat the link for a free open source, easy to use software that does not require coding, but it's based on R. It has R underneath, under the hood, so you can always go in and see what's going on. I like it because you can use it even just in the browser window. So you don't need to download anything onto your computer. You can do it from an iPad. You can do it from your phone.
Awesome. Yeah, just copied it. Thank you. Thank you for sharing the resources. And we would have to listen to your podcast. And what the good news, everyone, that next lecture is also by this amazing duo. And they're going to talk about a little bit more advanced statistics. Do you mind telling us what you are planning to cover?
This is the one in January. Yeah, we're going to actually cover some specific statistical tests and how to choose which test to use when, and a little bit about regression. And in the meantime, check out the podcast and like a lot of those topics we're talking about, but buffered with a lot of stories and boy talk.
Yeah.
Amazing. Yeah, incredible. Thank you so much. Thank you for such an amazing, very interactive, very engaging lecture. I was just like sitting and listening nonstop. So it's really, really impressive. Thank you. Thank you.
Thanks, everyone, for coming.
Thank you. Yeah, thanks, everyone. I know it's late there, and you have a lot going on, but it looks like everyone paid attention. So
yeah, everyone paid attention, answered questions, and people are giving you lots of hearts and bravo. Thank you. Thank you.
Thank you, everyone.
Thank you. Bye, everyone.
Bye.
See you in January.
See you in January. Bye-bye.